Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen. Welcome to this afternoon symposium session entitled Digital Pathology in Anatomic Pathology. I'm Dr. Arni Talib from Hospital Kuala Lumpur, and I'll be chairing with my colleague, Dr. Fauza Abdul Ghani of University Putra, Malaysia. Ladies and gentlemen, diagnostic pathology is entering into an exciting time with a more widespread use of digital imaging in pathology. In the last few years, we have witnessed an increasing use of machine learning, deep learning, and artificial intelligence tools making their way into healthcare as well as the diagnostic pathology workflow. To further enlighten us on this topic, let me introduce to you our first speaker of this afternoon symposium, Datuk Professor Dr. Looi Meng. Professor Looi, as she is fondly known to many of us, is Malaysia's inaugural National Distinguished Professor or Professor Ulung, positioned at the University of Malaya, where she holds a concurrent appointment as Senior Consultant Histopathologist. She studied medicine at the University of Singapore, pursued surgical pathology at University of Malaya, Royal Postgraduate Medical School UK, and Brigham and Women's Hospital US, and she defended her research doctorate at the University of Malaya. During her long academic career at she has served as Deputy Dean for Postgraduate and chaired UMMC's Medical Advisory Committee. Her research interests encompass amyloidosis, nephropathology, oncopathology, global pathology, and histopathological innovations. Professor Looi is a Foundation Fellow and Senior Fellow Academician of the Academy of Sciences Malaysia and has served in various committees both locally and internationally. She is the founding president of the Malaysian College of Pathologists and was instrumental in establishing pathology laboratory accreditation in Malaysia and the Pathology Act. She is also the former president of the World Association of Societies of Pathology and Laboratory Medicine, or WASPAM for short, and was awarded the WASPAM Gold-Headed Cane for leadership. Her contributions to research, education, and medical science have been recognized with several accolades, including the Panglima Jasa Negara carrying the title Datuk, Sri Indra Mahkota Pahang with the title Datuk Indra, National Science Award, ASEAN Outstanding Scientist Award, Merdeka Award 2016 for Health, Science and Technology category, and the most recent addition this morning, the 2020 CPATH Academy of Medicine Malaysia Lifetime Achievement Reward. Congratulations, Prof. Looi. Ladies and gentlemen, I will now call upon Professor Datuk Dr. Looi Meng to deliver her talk.
I would like to thank the organizers for inviting me to be part of this International Congress of Pathology and Laboratory Medicine. It is an honor to be asked to share my thoughts on this exciting topic of digital pathology in anatomical pathology. And I'd like to consider it as an enabler of artificial intelligence. Firstly, I'd like to declare that I have no conflict of interest in the presentation of this lecture, and I'd like to acknowledge that some of the material and slides for this lecture have been adapted from the various sources that are shown in this slide. For those of us who practice in anatomical pathology, we are aware of the three essential steps in anatomical pathology. Firstly, the processing of tissues into thin sections that will allow us to view them microscopically. Secondly, the tool to capture these images and deliver them to our eyes, that is the microscope. And thirdly, the histopathologist who looks at the images and tries to make sense of it and make a diagnosis. With regards to the first component, most of us are familiar with the standard histopathological processing, whereby biopsies and resection specimens are rendered into microscopic histological section for the pathologist to examine under the microscope. The H&E stain has been the mainstay of rendering these tissues and cells visible under the microscope, and this has been augmented by various types of stains, histochemical, immunohistochemistry, and in situ hybridization methods, which are now fairly standard in most histopathology laboratories. The significant advancements in the first component have been automation for tissue processing as well as for staining, and the development of companion diagnostics. With regards to the second component, this deals with the tools to deliver images to our eyes so that we can understand the images that we see. And this involves the use of light microscope or the optical microscope, which has been the gold standard for a long time, for more than a century. The crux of this lecture rests with the advent of the virtual microscope, which is now poised to challenge the optical microscope on the pathologist's desk, so that instead of looking down optical microscope, we would be looking at digital images on the computer screen instead. So this takes us to the era of digital pathology, and digital pathology has been defined in various ways. But in simple terms, it is the use of electronic images for diagnostic, educational, and research purposes in pathology practice. And the rationale of using digital images or electronic images is that these are easier to store and to annotate and to retrieve, and therefore more convenient than the conventional glass slides or photographs that we use in anatomical pathology. Many of us are also familiar with telepathology, which uses digital images, whether static or dynamic, transmitted across distances through the IT system or through the internet, that allows then many people to be looking at the same images and commenting on them at the same time. The rationale is that images can then be looked at by a pathologist and others from a distance at a site which is different or far away from where the images were first created. This is a brief history of digital pathology. We can see that the first analog video-based telepathology system came about only in the late 1960s. And many of us are familiar with this kind of system. We still use TV-linked or projector-linked systems attached to microscopes to project images for discussion. And that's something that I think most histopathology laboratories still have. It was a good 25 years before the invention of the first slide scanner to convert optical images into electronic or digital images. But after that, digital pathology actually took off in a great way. Within 5 years, the first automated high-resolution whole slide imaging system was developed. And soon after, there was FDA clearance for image analysis algorithms for cancer biomarkers. Then incorporation of whole slide imaging into the digital imaging and communications in medicine specification. The College of American Pathologists came out with guidelines on validation in 2013. And 2019 saw the first FDA-approved digital pathology system for primary diagnosis. Granted, this was only for FFPE, histopathology, and it's based on non-inferiority of images produced by whole-slide imaging versus glass slides. But by 2020, good meta-analysis studies have shown good concordance in interpretation of images from whole-slide imaging as compared with glass slides. So the advent of digital pathology and digital microscope is tied up with whole-slide imaging. And this involves scanning of glass slides to convert optical images to digital form, and then navigating these digital images using computer software so that you can look at these images at any power, low power, high power, zooming up and down, and of any specific area of interest in these images, just like a glass slide, except that you use a computer screen instead of a glass slide. There are many scanning systems available as listed here, and really the suitability of these various scanners depends on what you want to achieve and what your workload is. We can immediately see that there are many advantages and applications in using digital images. We know that glass slides are a challenge because they take up a lot of space to store. They can be broken, they can be lost, they can be misfiled. And also, when you finally retrieve a glass slide, the section on it may have faded and it's not visible anymore. They're hard to retrieve and difficult to share. And digital images can address all of this and are far more convenient. I think most of us are very familiar with using digital images for conferencing and education. We are used to now using digital images for slide seminars, for multidisciplinary discussions, certainly for teaching, for standardizing training, and even for remote consultations and for EQA. We know that now many of the images that are the material that we receive from external quality assurance programs come as digital form, and that allows even small biopsies to be included in the EQA repertoire. There are also other applications for using digital archives, not only for quality assurance and consultation, but certainly for comparing archive biopsies with current biopsies, even if the old biopsies may be more than 10 years old, and also for research and publications where we could then retrieve digital images which are still very visible for publication compared to pulling out slides that may be stored for many years and which may be faded. And there may be many other applications which many of us may be familiar with to add to that list that I've just mentioned, which is not exhaustive. But one of the most important applications is that e-slides are easily integrated into the LIS and into the electronic health record. And such a digital workflow would improve collaborative efficiency across disciplines, across the different medical disciplines, and that can only lead to an improvement in patient care. So, in spite of all these obvious advantages that I have mentioned, we ask ourselves, how widely is digital pathology used today? Certainly in Malaysia, we are quite familiar with using digital pathologies in education, in conferencing, and so on. But it's good to look at this study from the UK, which was done in 2017, which asks certain questions. I just picked two of them. To what degree does your institution use digital slides in the following scenario? And you'll find that there is generally good acceptance of digital pathology for teaching, postgraduate teaching particularly, and for research, but less so perhaps for diagnosis. And to the question, what are the current barriers to wider digital pathology usage in your institution? It looks like some of the major barriers is the financial costs of a digital pathology setup, the time involved in doing digital pathology setup, as well as some mindset issues that it is not perceived to be useful by many of the departments that were surveyed. So it means that while there are many advantages and applications in digital pathology, that there are still many challenges to its usage. And guidelines from various professional bodies help us to appreciate this. And there are many guidelines from the College of American Pathologists, from Digital Path Society, and so on, including the Royal College of Pathologists of UK. And this deals with many aspects. The use of the in-house validation system, the importance of a good mix of cases and stains when we validate the systems, consideration of the technicalities involved, the hardware, the software, the type of scanners, the resolution of our computer screens and our storage systems and so on. And certainly a lot in the work processes, the investment that has to be made. Is it cost effective? Is it sustainable? And also knowing that you have to have a dual system, because firstly, the digital system depends on capturing images from an optical system. The integrated workflow is also something that has to be carefully worked out. There have to be staff mindset changes and adaptation, and there are also occupational health issues that are different, because spending hours in front of a computer screen can have certain issues to health. There are also regulatory and data security issues, as well as legal issues involved in whether we can really report, make a diagnosis on an on a digital system. Nevertheless, I think that we can see that the COVID pandemic has been a great boost to the digital pathology practice, and because it does provide some solutions to social distancing and to working from home. And many of us now easily adapt to remote or online communications. And I would see that there's a great future for rapid adaptation of digital pathology in practice. So let us consider the third component in anatomical pathologists, and that is the histopathologists or the anatomical pathologists. And in this, the pathologist has to develop skills, knowledge, and judgment in the interpretation of images to bring about a clinical relevance to the histopathology study of images to make clinical diagnosis that is clinically relevant. So the question is, can artificial intelligence take over some, if not all, of the functions of the histopathologist? The advent of artificial intelligence in histopathology or anatomical pathology has been dubbed as the third revolution in anatomical pathology. And it is made possible by digital pathology and whole-slide imaging, which lends itself to image analysis and to machine learning and the innovations related to artificial intelligence, such as the deep neural networks and so on. The rudimentaries of image analysis involves basically a few logical steps. Firstly, the extraction of features from images to identify the object that we want to study. the segmentation of these objects from the scene, from the histological slide, and the measurement of these isolated objects, and then the analysis of these measurements. Nowadays, there are numerous software available to do image analysis and to automate it. And these are available either commercially or open source. So we don't have to go through those tedious processes that I've mentioned in my previous slide. And many of this software has been applied to the grading of cancers and classification of tumors, as well as to automate IHC scoring for various tumor biomarkers, such as ER/PR HER2 in breast cancer. But artificial intelligence is a step further from image analysis. The question is whether machines can perform smart activities close to what the human does. Can it provide not just data, percentages, and counts, but actually lead to decisions, lead to a prediction of a diagnosis or a clinical decision? So linked up with this is training of the machine learning, and numerous innovations in artificial intelligence, such as deep learning. But rather than going into details on this, which I'm not qualified to do, I would like to share with you an attempt at artificial intelligence at my department in collaboration with the Multimedia University. This is just a small experiment that we did a couple of years back as a master's project, as well as a PhD project in MMU. And I'd like to acknowledge my co-investigators, Dr. Jenny Lee and Dr. Kaur, who are now graduated MPath students and working as pathologists, Prof. Teo from my department, and Prof. Muhammad Faisal from the Multimedia University. We just set up with a simple objective of using artificial intelligence for estrogen receptor LRAD scoring in breast cancer patients. And I think those in anatomic pathology would be very familiar with LRAD scoring. This is a routine assessment by histopathologists of breast cancer tissues and cells, and uses this fairly time-consuming, mundane, tedious process of counting cells and determining what percentage of breast cancer cells express ER and what intensity they express them at. And because it is so tedious and time-consuming, it is prone to inter-observer and intra-observer variability. The methodology we used in this simple experiment was to use 40 ER stain whole slide images, and taking from this 30 images and just taking a small area of 30 images to develop the ground truths for training the machine. And to develop this ground truth, the pathologist would annotate every slide within this small area to determine to indicate which cells are tumor and which are not, and to indicate of the tumor cells which express ER and at what intensity, using different color annotations. So based on this ground truths, the machine learns how the pathologist determines which cells are tumor and which are not, and which are ER positive, and so on, and applies this ground truths to all 40 whole slide images that the machine is asked to examine. And we compare the LRAD scoring by the machine on the 40 whole slide images versus the 40 glass slides. by the histopathologists. And the findings have been very encouraging in that, although this is a fairly crude and initial investigation, and the software is just a very initial prototype, what we found was that there was a fairly good concordance in terms of clinical decision-making categories determined by the pathologists compared with the machine. The concordance actually was pretty good. But we learned also what the false positive results were due to and what the false negative results were due to. So there are many technical challenges that we realized. Firstly, annotating images or training the machine is time consuming. It needs experts who, however, are very busy to develop the ground truths. And developing the ground truth is not always easy because we need to be very certain about what we consider positive and negative and what are tumor cells and what are not tumor cells. There are also technical challenges in terms of the quality of the glass slides, or rather the optical images. And there's the dimensionality challenge of dealing with large gigapixel images, and also with patching to ask the machine to apply to the whole whole section when we're actually just annotating a patch. Of course, we begin to appreciate the financial limitations of such a system. There are also communication challenges in using an artificial intelligence system. As it stands, the machines tend to use a binary language versus a clinical language. And in the clinical language, you do not just say positive or negative, but there are always nuances and gray areas depending on the situation of the patient. Also, machines tend to be unitask versus multitask, which most humans are. And as an example, if a machine were to come across a granuloma in the digital slide, it would probably just not bother with it. It will go on faithfully looking at the LRED score, whereas a pathologist would stop and say, goodness, there is a granuloma here, which is caseating, and I want to do a ZN stain. So this sort of ability to multitask and look at things from different angles is still some way off for the machine. And certainly, humans are very suspicious of how the machine comes to its conclusion. We call that the black box issue, because we like to usually have some reasoning as to how a conclusion is made. Whereas right now, we're not exactly sure how the machine actually learns from us to decide whether a cell is a tumor or not, or whether it's ER positive or not. So clinical decisions have a lot of fine-tuning and a lot of reasoning and discussion attached to it, which perhaps the machine cannot quite achieve yet. But this little experiment has taught me that there is a lot of future in artificial intelligence. And in spite of the technical challenges, certainly I can see a great deal of value in having artificial intelligence or the machine to take over the tedious tasks of grading and counting biomarker scoring in histopathology practice. And certainly a machine would be better at it than we are because they would not tire and they would be very consciously counting instead of what we do, which may involve some shortcuts. Certainly, there's a lot of future in artificial intelligence in research and innovations. And there are already a lot of studies looking at the tumor microenvironment and of measuring and quantifying various targets in multiplex immunohistochemistry system, which artificial intelligence is going to be far better at than the human eye. So does that mean that artificial intelligence will be able to do so much that the analytical pathologists will have very little left to do? Well, I would think that there is really no cause for alarm. I always say that, remember, garbage in, garbage out. The pathologist is required to make sure that no garbage enters the system, and we are going to be extremely important in quality control to look at the quality of the slides that are scanned in the whole slide imaging system, the validation of system, and to look at the meaning of the generated data, and finally, the interpretation of this data for clinical practice. The pathologist is also going to be extremely important in machine training and algorithm development. The ground truths finally come from the pathologist. So does the clinical direction, developing the optical pathology workflow, and maintenance and ongoing evaluation, and developing the policies of how the laboratory will be run with the aid of artificial intelligence. So thank you very much for listening to me, and I look forward to a discussion on this topic. Thank you very much.
Assalamu alaikum and salam sejahtera, and a very good afternoon to everyone. I'm Dr. Fauza and I am co-chairing with Dr. Arni for this symposium. Thank you to Prof. Dr. Looi Meng for the very informative talk. And from her talk, it's a big relief that pathologists will not be out of job to ensure the quality of the diagnostic works in anatomical pathology, and artificial intelligence is an aid to assist us in our pertinent works. Okay, now I am honored to introduce our second speaker, Dr. Eddie Sungji Huang. He is currently a Solution Architect Director, Healthcare Asia Pacific NVIDIA. He has vast working experiences, which include Chief Technical Officer at Everfortune.ai, Solution Architect at Headquarters of NVIDIA, Director of Artificial Intelligence Center at China Medical University Hospital, Taiwan. He was also a full professor and Dean of Student Affairs, Medical School, China Medical University, being part of the medical physicist team, radiation oncology at Moffitt Cancer Center, USA, and had been in radiological sciences, University of Texas Southwestern Medical School, United States of America. Dr. Huang was educated in several professional domains, including artificial intelligence, electrical engineering, medical physics in clinics, which makes him a good candidate in administrative management for development and innovation in the healthcare industry. His clinical experiences allows him to fully comprehend the needs of the healthcare industry, while his academic research trains him to develop new technologies to solve problems independently. These professional experiences with expertise makes him a good solution architect and understand the healthcare ecosystem very well. So I now present Dr. Eddie for his talk on artificial intelligence in medicine. Please welcome.
Hello, welcome to International Congress of Pathology and Laboratory Medicine 2021. Today's presentation is going to introduce how NVIDIA Clara computing platform helps AI development in different stages and the perfections of the healthcare industry. I am Eddie Huang, working in NVIDIA Solution Architect team, and it's a great honor to be here. Today's presentation is first to follow current situation and the challenges of the AI development, especially transiting pathology into the digitization. AI and COVID pandemic speed up the digitization revolution in most of fields, including pathology too. Next, NVIDIA Clara, which is the collection of the accelerating computing SDK for healthcare application, will be introduced. Last but not least, the current development in computational pathology with successful application will be also included. This is an amazing time in computer industry in the world. AI becomes the most powerful technology force of our time. AI is written the software that achieve results no human written software can. The scalability of this approach has started a race to create an ever larger, more complex, and more capable AI. Computation required to train state-of-the-art model has increased 30,000 times in less than 5 years, which means doubling every couple of months. The capability of AI is incredible. Convolution neural network and a transformer are the core of AI for computer vision and natural language processing, which both have many applications in image recognition and semantic analysis. Now, computer can see and can understand the real world through the data transforming. AI is all about connecting models in series sequence together. To understand AI, we need to understand how to generate AI model first. The way to create AI model is quite complicated through working together in 3 individual fields, including algorithm for data scientists, computing for IT, and big data from the domain know-how. Choosing the suitable structure of the deep learning neural network to train the parameters will be the one challenge. That might be thinking of the UNet for segmentation. But how about the DenseNet 1-to-1, BGG19Net? There are so many more hyperparameter selections. Without performing so many try and errors, there is always not for sure. On the other hand, computing management about the GPU or multi-GPU, multi-node, in cloud or the local machine, on-premise, to balance the IT resources to support data scientists are always struggling. It really depends on the situation at that moment. To avoid the data garbage in and garbage out, domain experts need to spend a lot of time on data labeling, grouping in order to make sure the data input, as we expected, is very clean. With all of it working accurately together, the precise and useful model can be generated. Clinically, there are about 2,000 differential diagnoses listed for the imaging finding in whole body. which causes 7,000 entities and 55,000 models are also needed for the AI to do the screening. Currently, there are only 76 FDA approval AI algorithms. I guess the jobs in more and more model generation are still desirable for AI ad screening inside hospital. In here, we still can see the numbers of the AI model is highly demanded to be used in clinical. The key, the model has to be adaptive is the one different concept as compared of the traditional mathematical method to provide an accurate function, including recognition, classification, and the prediction by using computer. So continually deploy and integration of AI model into workflow is one of the issues that we need to think of it. Before, medical information from the patient is directly going to the physician. Now, the things and the workflow are different. We have to think of the AI computing machine is how to work into the hospital IT together. In clinical, we say patient is the center and the service are all around the patients. Now, AI model becomes the center of the IT, and all the equipment has to accept the new machine running AI to be connected and to be forced working together. Therefore, it comes the incredible computing challenge like an enormous model and a training data set. That puts the limit of every aspect of the computers, storage, and networking, infrastructure management, force issue on I/O, running time, latency, and so on. If we look back 20 years, we will have seen radiology in a similar transition process when they move away from the analog film X-ray to digital images. Today, digital radiology is popular, and we expect the same to be true of the pathology in the next few years. This presents a great opportunity for all sorts of groups, from the AI startup to established OEMs. COVID-19 has probably helped our causes because certainly everyone working from home and see the value in digitization. Moreover, AI is a pull-through technology for the digitization. When radiology went digital, the cost saving was very clear. For pathology, you still need a slight preparation, for the economics are less than clear so far. AI is valued up for the data going to digitization. Several promising research encourage the development of the digital pathology with deep learning applications. This year, MICC AI conference, including around 40 papers related to computational pathology. Several methods are proposed to learn from the unannotated dataset, which can be transformative. New methods proposed to reduce the time taken to process the whole slice image to more clinical feasible levels. Combining clinical nodes as well as the genomic remains beyond the scope of the most team, although the TACG archive has produced some interesting work. As per many other modalities, GAN has been shown to have the many use in histopathology, especially for stent normalization. Here shows the key challenges of the digital pathology. For one single file is around 100 gigabytes. Size is always the huge challenge in digital pathology in any way. Even though we just want to move the one data from a place to another, it will still cost a lot of time to deliver it. How about the labeling? If we get 1,000 images per hour, how we can see through all the detail by human beings' eye? It's not just possible, easier for us to do that. In NVIDIA, we devote ourselves into the computing accelerating, starting from the GPU chip design and the optimized software from CUDA coding and CUDA-X library for different applications. CUDA is a parallel computing platform and programming model developed by NVIDIA for general computing on GPU. With CUDA, developers are able to dramatically speed up computing applications. The software stack for AI in accelerated computing is complex. The stack for each domain are different, like rendering is different than the genomics, different than the deep learning. So the stack for each computing environment is also different. NVIDIA is providing a computing platform with full stack of software for data process, feature engineering, model training, and inference. NVIDIA created SDK to help developers to power the GPU computing to make it easy working on the AI model and efficiently developing workflow. We even have the system architecture for high throughput and high interconnected bandwidth to maximize the neural network training performance. Not only we have the local machine with you, but also we provide the cloud service, which is NVIDIA GPU Cloud. NGC is our cloud for the containerized stacks, always up to date and always optimized. NGC is the right place to support you to install the right software and the containers, libraries, and the tool for your specific environment with working with GPU. NVIDIA Clara is a health application framework for AI-powered imaging, genomics, and for development and deployment of the smart sensors. It includes full-stack GPU accelerated library, SDK, and reference application for developer, data scientists, and researchers to create a real-time, secure, and scalable solutions. For pre-trained model, the AI-assisted labeling will semi-automatically generalize the ROI ready for modification by physicians. Optimized AI training framework based on the multi-GPU scaling and new feature including AMP and smart caching mechanism will accept more than 20 times in model generation. When data is not generalized enough, collaborative learning framework, including the technologies such as the federated learning and transfer learning, enable data scientists and researchers to co-work with the other data resources by keeping the data privacy and the security together. For scalable deployment, our Triton inference server is a graph optimizer that targets the inference service while optimized for a bunch of the computing constraint and accuracy and data flow through response time and memory size. There are so many features in the Clara application framework. Today, for the digital pathology, I'm gonna focus on AI-assisted annotation and the pre-trained model and the I/O adapter scalable inference. First, I would like to introduce the nuclear segmentation pipeline, which is one of the reference pipeline provided with Clara Deploy SDK. It accepts the OpenSlice image format. The output is color image, where the cell nuclear segmentation results are overlaid on the top of the original image. The result image is published to the render server so that it can be reviewed on the web browser. As part of Clara 4.0, we are going to introduce our very first pathology model plus training script, new pre-trained segmentation model that can detect metastasis in whole slide image, which is built using the Canadian 16 open dataset. Currently, we focus on the mention for building the SOTA, which we have done and focusing on improving training performance. We will also have the optimized training pipeline for building similar model used for the nuclear segmentation. The pipeline will include our new efficient data loading library called CuCLA Image, which can reduce the whole slide image inference time from the 11 minutes on CPU to just 13 seconds on a V100 GPU. Kukla image is an extendable toolkit designed to provide GPU-accelerated I/O, computer vision, and image process primitive for n-dimension imaging with a focused biomedical imaging. It facilitates efficient I/O for image acquired from the modalities such as digital pathology, CT, MR, and processing of such image efficiently with CUDA-based primitive. The plan is to offer both C++ and Python APIs. On the right side, the performance with reading file by Kukla image as compared with the open slide in number of threads is presented. Here shows we can get at least 4 times faster while using Kukla image toolkit for reading the pathology files. Here are 2 successful stories that I can share by using GPU to achieve the goal in digital pathology. PATH AI using the NVIDIA GPU trained a convolutional neural network on over 500 pathology images of the breast cancer tumor to classify the tumor with grade and histology subtype. Moreover, AI Fourier team that tests the neural network accuracy on separate set of the 300 images. Their algorithm was able to distinguish between the low intermediate versus the high-grade tumor with 82% accuracy. Both stories are pretty encouraging. Here is one example to see how we can compose several operators into a meaningful pipeline as the one AI. Clara deploy has 17 of these today. But coming back to our COVID-19 example, this is the reference pipeline that reads the lung CT study from the DICOM file and segment the down, excluding the first inference servers on Triton, and then apply the classification on the chat CT with the second inference of this pipeline. You can then visualize the information with cloud deploy render server before you push it back to the PAC system. A couple of important notes here. There are 2 different AI algorithms within the same pipeline. To inference on Triton, for operators, you can go as much as you can if you want to put more functions into to become the one AI. We have successfully used around 10 different models becomes a one pipeline today. There is nothing avoid you to consume the multiple payloads and apply the inference at scale. Medical data related to the physical or mental records is highly sensitive and is considered as personal privacy, which is not able to leave from the hospital without the patient agreement. NVIDIA Clara Federated Learning provides the framework to running the model training together without sharing the data and build up a more generalizable AI model regardless of the location, patient population, or the data size. Lately, we have finished a global project that 20 hospitals in 20 days to build up an AI model that predict the oxygen needs while a patient comes into the ER. Turns to support AI in pharma, NVIDIA Clara Discovery combines the power of the accelerated computing, AI and machine learning to supercharge the entire drug development process, like unlocking the potential drug to market faster. Clara Discovery provides the GPU accelerating genomic analysis in variant coder. Moreover, using the breakthrough in computer science, we can bring it use the simulations in silico method to understand the biological mechanism of the proteins that affects the diseases and search for the leading candidate drug before the slow process in vivo test. Due to the pandemic, the need for smart hospital has never been more urgent. Smart sensors can act as the eyes and the ears to make sure safety and operational excellence in clinical, such as the temperature screening and the protective gear detection, safe social distance, NVIDIA Clara Guardian is an application framework and a partner ecosystem that brings the smart sensor and multi-model AI together to improve the patient care in healthcare facilities. Many of the NVIDIA features SDK that I just mentioned, but all the NVIDIA useful SDK and framework joined together become the one turnkey named by Clara, which fits into the entire AI workflow smoothly and accelerate the development too. Taking the clinical hospital as a working scenario, deployment will be something like this. Get the data from the relevant medical instruments and hospital system through the PACS or RIS system. Execute your pipeline and get the result back from the computing server. Also to be visualized on the PACS viewer for physician to run the modification to refine your model for the next stage. That will be all my presentation for today. If there is any question regarding the NVIDIA Cloud Computing Platform, please feel free to share with me. Thank you so much.
Thank you, Dr. Eddie Huang, for the very informative and exciting discoveries and new developments of artificial intelligence in medicine, healthcare, and diagnostic services. Very impressive, considering the vast background of mathematical algorithm and While there are many setbacks from COVID-19 pandemic, it certainly does one good thing, which is boosting artificial intelligence in medicine to improve patient healthcare and healthcare facilities. Now I would like to briefly introduce a long and impressive CV of Associate Professor Dr. Shahnorbanun Sahran, which I hope would do justice to her. She earned her PhD in Intelligent Control Systems from the University of Cardiff, Wales in 2007. A Master Science degree in Quality and Productivity and a Bachelor in Statistics from University Kebangsaan Malaysia in 1995 and 1994 respectively. She is an experienced lecturer, researcher, and previously was the chairman of Center for Artificial Intelligence Technology, Faculty of Information Science and Technology, University Kebangsaan Malaysia for 7 years, since 2013 to 2019. She specializes in machine learning, optimization, and IT in manufacturing. Driven by the boost of digital transformation ecosystem, she takes pride in providing the best possible advance and adoption of artificial intelligence technology in healthcare. Her passion for artificial intelligence in healthcare can be tracked back to 10 years ago, where she spent a significant time working on artificial intelligence, particularly machine learning and healthcare, focusing in diagnostic services. In addition to her primary job functions, she has been actively involved in many regional and international platforms, sharing her expertise in artificial intelligence and healthcare. She has published many articles and books and have supervised many master and PhD students. Without further ado, I would like to invite Associate Professor Dr. Shahnorbanun Sahran to share her topic, the utility of artificial intelligence in diagnostic pathology. Please welcome.
Assalamualaikum. Very good afternoon. I'm Shahnorbanun Sahran, a researcher or associate professor from Medical Computing Lab and Machine Learning Lab under Center for Artificial Intelligence Technology from Faculty of Information Science and Technology. Today I would like to share my talk about artificial intelligence in medicine. Artificial in medicine already started more than 30 years. If we look at this journal, Artificial Intelligence in Medicine, the first issues is in 1994. And until now, this journal is still popular in publishing papers for artificial intelligence in medicine. Okay, so looking at this journal, we know that artificial intelligence already started long time ago. Okay, and at that time, the focus is more on expert systems. These are the top 10 hospitals in the world I would like to share with the audience. They are Mayo Clinics, Cleveland Clinic, Massachusetts General Hospital, Toronto General Hospital, and hospital in Berlin, Johns Hopkins Hospital, and also Hospital of Zurich, Karolinska University Hospital, Singapore General Hospital, and also Sheba Medical Centers. These are the top 10 hospitals in the world. The ranking are based on recommendations from medical professionals, which result from patient surveys and key medical performance indicators. These top 10 hospitals in the world are using AI in their daily tasks. Okay, if we go to a few important person that involved in these 10 top hospitals, such as a Mayo Clinic CIO, he said that this artificial intelligence stuff is real. Okay. In his talk, he mentioned that whether it's voice recognition, geographic information service, or automated, or any other of a host of nifty AI tools hidden away in smartphone and mobile devices, there's a significant number system that impact his life all the time. And that is what we call AI, which keep his life functioning well. Chris Ross is very particular about technology. He's very supportive, and he used to doing support AI, artificial intelligence in medical research. If we look the next slide, this is Mass General Constant Cornel Lehman. Okay, he's a professor of radiology at Harvard Medical School and co-director of the Avon Comprehensive Breast Evaluation Center. He also mentioned that the pathway forward is clear, and we are eager to advance their work by continuing to combine the powers of AI and medical imaging. He mentioned in his research, why is it important to have better breast cancer risk assessment tools? Okay, so these are, based on their research, it helps more than 80,000 Mass General patients, okay, using AI. Okay, National University Hospital Singapore also is bringing AI to clinical implementation at NUHS. Okay, they are focusing on AI vision in healthcare, clinical AI development process, NUHS DataMart phase 1 and phase 2, which consists of data source, data warehouse, and presentation. And for clinical tools, they are working forward for automated diagnosis of appendicitis based on clinical notes, and also Singa Dragon, longitude analysis of a population's electronic health records. And the third one is readmission prediction using deep learning. So we can see that National University Hospital Singapore is also bringing AI to clinical implementation. The next one, our neighbor Thailand, also have practical applications of AI research framework. If we look at this slide, we can see that they have a house of what we call practical applications of AI research. Yeah? So they have speech technologies and healthcare, which they call WAJA, and they also have cyberbrain, and they are very committed to do a collaboration among universities, private organizations, and the government sectors in order to come up with a very good smart health, smart education, smart tourism, smart energy, smart home, and also smart agriculture. Okay, this is our one of our team output or research that we have done, but this one is focused on radiology. So we are doing some research on machine learning methods for breast cancer diagnostic, machine learning methods for prostate cancer, for histopathological images. And we also are doing research on blood cells cancer. This is my involvement for Digital Pathology Congress. Okay, in 2018, I presented a paper. It's about prostate cancer diagnosis for Gleason grading. Okay, this is the output for what we have done for after few years doing research with collaboration with Hospital University Kebangsaan Malaysia. And during the Digital Pathology Congress, we have our one of the researcher from Canada, from Grenada University Hospital, Juan A. Retamero. He presented their experience of 100% digital pathology in primary diagnosis at Grenada University Hospital. Grenada University Hospital already implemented 100% digital pathology since 2016. Okay, this is a rough idea that they share the pathology laboratories at Grenada University Hospital, Spain, which comprise 4 different sites. So they have 4 campuses there. If you can look at the slides, they have Campus de la Salud Hospital, they have Bazaar General, Montreal General, and also VNH. Okay, these are the 4 hospitals that work together to adopt digital pathology. I believe that for the Grenada Hospital University, they use hub and spoke model, hybrid hub and spoke model. Okay, the traditional model that normally or usually hospital are using is hub and spoke model. But this model, using digital pathology, it can use hybrid model, where you can see from the slide, this is the hospital, okay, and all the other can say pathologists from other any workstation, they can share or they can send their slides to the hospitals, and also maybe the hospital can send to them, and then they can send to the hospital. This is what we call a hybrid hub and spoke model. It's no more like the traditional one where only from hospital they will send the images to the others. Yeah. Pathology in 21st century. So there are 7 components that we need to look at for pathology in 21st century, which are electronic medical records, complex molecular diagnostic, quantification algorithms, interface automated laboratory testing, post-light imaging, artificial intelligence, and computer-assisted diagnostic. So we are expecting for pathology in 21st century, and I think this is happening now, shortage of pathologists around the globe, coverage of larger geographic territories, clinical trials, aging population, complexity of workflow, research, consolidation of laboratories, quality assurance and quality control, and also education. This is research done by Toby Cornish. Okay, based on his research, we can see that the year of publication that focus on digital pathology or virtual microscopy or whole slide imaging or whole slide image is dramatically increasing since 2010 until 2017, and I believe now it's keep increasing. Okay. The future of pathology, digitization of pathology, where it will direct us to big data, subspecialty pathology with whole slides imaging, correct and actionable data, And from here, we can go for computer-assisted diagnostic and at the end, integrated pathology. This is the future of pathology. So for this talk, I'm going to concentrate on AI is transforming digital pathology. So here there are four utility that we will concentrate on. The first one is patient-centric treatments, improve efficiency, positive changes to workflows, and more time devoted to cases. So before we go to AI is transforming digital pathology, we will discuss about what is AI. Okay. AI can be defined as identifies intelligence with adaptation, with insufficient knowledge and resources, which implies that the system is finite, works in real time, is open to novel tasks, and learns from experience. This is an illustration of AI. Okay, AI is a biological neural network. Okay, it tries to mimic the intelligence of human brain. This is a schematic diagram of our brain network. Yeah, and this is a computerized network. So this is the input, hidden, and output. This is what we call the architecture of neural network, one of a very famous artificial intelligence technique. In terms of terminology, artificial intelligence can be, there are a few levels of artificial intelligence I can say. The first one is artificial intelligence, where it concentrates more on ability to sense, reason, engage, and learn. The second layer will be machine learning with its ability to learn. So for machine learning, we focus on supervised learning, unsupervised learning, and reinforcement learning. The third one will be methods where we focus on ability to reason. Okay, and one of the popular methods is regression. So the last one will be the technologies or physical enablement. Okay. Types of artificial intelligence. So machine learning is very popular in artificial intelligence. When we talk about machine learning, we normally talk about deep learning, predictive analytics. Yeah? And there are a few others under types of artificial intelligence, which is natural language processing, speech, expert systems, planning, scheduling, and optimization, robotics, and vision. So these are all types of artificial intelligence that can be used for specific tasks. Machine learning, learning from experience. So looking at this example, so we can have whether unsupervised learning or supervised learning. Okay, if we are talking about supervised learning, meaning that we are labeling the data. So this data will be fed to the computer and we are using a learning algorithm to extract features and then select features and let the machine learn and do some predictive model. And at the end, we will get some output. This is a very simple example how it works for supervised learning. Let's see, we have 4 coins here, for example, 4 samples. We have 5 cents, 10 cents, 20 cents, and 50 cents. So in this example, we can use the size or the diameter or the weight as the features and the value as the label, okay? Let's see for 5 cents, the weight is 3 grams. So this information will be fed to the computer and using machine learning algorithm, we will train the algorithm to identify and then determine and then classify these data, and the output will be 5 cents if the weight is 3 grams. So basically, when we talk about AI or machine learning, the data itself play an important role in order for us to get good results. This is one of our team members' work on machine learning for prostate histopathological grading. So from this slide, we can see that on the top there, we have histopathological images. It's like a pool there. And then from there, we do segmentation to get 4 different classification: lumen dataset, nuclei dataset, cytoplasm, and also stroma dataset. And from these 4 tissue components, we extract the features from each of them, and we do feature selection. We select only the important features, and from there we pass the information to the machine learning algorithm, and at the end we combine or we assemble all the information to get the result. So the step for feature selections with SVM is where the intelligent decision making in diagnosis and grading prediction using support with the machine is taking place. Yeah. So AI is transforming digital pathology. So there are 4 main concerns here. First is patient-centric treatments. DP, which is stand for digital pathology, could potentially improve the quality and speed of patient care. One of the benefits is a pathologist can look at a whole slide at once, then choose to zoom in on an area of interest. In contrast, a conventional microscope does not allow for looking at an entire tissue sample. So as a human, such fragmented views can cause pathologists to miss things. Okay, so AI and digital pathology help professionals make more informed conclusions about patients. AI can analyze data quickly, early detection is possible, and meaning treatment can begin sooner. AI in digital pathology also has the potential to radically change the patient experience with apps and mobile devices, giving them direct access or better and faster communication to their medical expert. So what will be our next action? The next action is to integrate digital pathology information and patients' clinical and omics data to make novel information accessible to the clinical team, which gives the pathologist augmented ability to deliver patient care. So here we see that the digital pathology and AI was a key component for advancing personalized medicine. The second one is improve efficiency. Digital pathology allows looking at several images side by side. So this option could be particularly useful when looking at multiple pictures of tumors or over time. This is for example. By combining DP with image analysis and AI, it will lead to improved quality and efficiency and transforming pathology data into clinically actionable knowledge. It allows pathologists to look deeper into the data than ever before, and to get more information and quantify the information by automations. Okay, when we talk about look deeper into the data, we can use predictive analytics to prepare and pre-process the data. We can do data integration, we can do data selection, we can do data cleansing, data reductions, data transformation, and also we can at the end do data mining. These are some predictive analytics model that we can use for the data. Okay, we can do classification or prediction, we can do clustering, trend analysis, deviation detection, association, or sequential rules mining. There are a lot of other models that we can use to look deeper into the data. Okay, at the end, we can come up with predictive analytics that model the data such as patient admission, electronic health, satellite data, environment data, new treatment plan, new mitigation, and improve the quality of the service using machine learning and statistical approaches. Okay. The next one is how to look deeper into the data is looking at the descriptive, predictive, and prescriptive. There are 4 types of data analytics. Yeah? The first one is descriptive. So what is the data telling you? What's happening in my business? Yeah? The next one is diagnostic. Why is it happening? Okay, so we have the ability to drill down to the root cause using the data that we have. The next stage will be predictive. What's likely to happen? So business strategy have remained fairly consistent over time. Yeah? Historical patterns being used to predict specific outcomes using algorithm, and decisions are automated using algorithms and technology. So the next step or the important step will be the prescriptive. What do I need to do? So recommended actions and strategies based on champion or challenger testing strategy outcomes. Applying advanced analytical techniques to make specific recommendations. So these are the output that you can get from looking deeper into the data. So just imagine if you have a huge amount of data and you do some predictive analytics, you can predict and you can prescriptive, you can plan in advance what you need to do. You can form a good strategies. Yeah. Okay, the third one is about positive changes to workflow. This is an example of pathology's workflow. Okay, from this workflow, using AI, we can integrate the process with artificial intelligence or machine learning. So the green box indicate the process that we integrate with AI. So just imagine with this integration, by combining AI and digital pathology, a digital workflow creates opportunities for better management of a pathologist's workload. There are opportunities to improve pathologist's workflow, releasing up to 13% of every pathologist's time. This is based on some research that have been done. Okay, the last one will be more time devoted to cases. With digital pathology combined with AI, yeah, it seems that seamless cloud-based storage and apps, computational pathology, where AI applied to pathology, one-click experts consultation, one-click transfer of care, automatic load balancing across institutions and labs, local, regional, and national digital pathology exchanges. So with all these facilities, pathologists can spend more time devoted to cases. Yes, AI is a key component to digital pathologies. However, there are some barriers to digital pathology adoptions. One is regulatory, financial, technical, and the culture within the discipline itself. So these are four main barriers that we need to look at before we started to adopt digital pathology. If you're talking about cost, yes, for the first time, if you want to adopt digital pathology, it involves a lot of cost. However, if you look at this graph, this is a graph presented by Joanne from Grenada Hospital University. So it mentioned that with a 5% productivity improvement, the costs are never recouped. With a 10% productivity improvement, the costs are recouped by year 2. Okay, that means after 2 years, you can recoup the cost. Okay, with a 15% productivity improvement, the costs are recouped by year 1 only. So the model assumes all improvement in pathologist efficiency can be recouped as a financial gain. So if you're thinking about financial or what cost, then look at also the benefit of gaining the productivity. So what's next? So based on the information, we can see that today there's a huge amount of data far beyond human capability to handle it. Computer speed, storage, with cloud facilities and sophistication is maturing, and the whole digital ecosystem is in favor of digital pathology adoption. Because AI is neither astute nor intuitive, physicians will remain essential to cognitive medical practice. So why not we move together for a better living? Thank you. That's all from me.
Thank you very much, Associate Professor Dr. Shahnorbanun Sahran, for enlightening us of this surely expanding future of unlimited boundaries, especially in the utility of artificial intelligence in diagnostic. As Prof. Dr. Jo Martin mentioned this morning in her K. Pratap Memorial Lecture, quote and unquote, the future is another country. We need to keep an open mind, being optimistic, willing to adopt and adapt these new opportunities to enable us to progress with the advent of technology. Okay, so now we are in our Q&A session. And I invite Dr. Arni to ask questions from the delegates to our distinguished speakers. Okay, maybe I will start off first. There is a question from Chan Kai Soon to Associate Professor Dr. Shahnorbanun. Since AI applications rely so much on data set as the basis for making decisions, will any change in the current tumor grading schemes and staging criteria, etc., invalidate AI decisions based on older data sets? Thank you.
Okay, thank you for the questions. I can start now, yeah?
Okay, based on our experience, when we start doing data collection for histopathology cancer data set or radiology, we need to involve the expert. So when we involve expert, we need to involve more than three, so that we will have fair. So if two said no, then the other will say one, or two said yes, the other will say one. So we have a fair vote. And I think this was question to me during my Tokyo. The same question goes to me: what if the pathology make mistake? Because you need to involve pathologists in the preparing the data. So what if the pathologist make mistake? So I told him that yes, people might make mistake, but that is why we need to have more pathologists to validate the case. Okay. And if we are talking about machine learning, although it depends on the data that we have collected, but still there are evaluation criteria that can be used. Yeah. For example, let's say we use in medical, not only accuracy is important, but also sensitivity. So there are certain threshold and value that can be accepted. For example, if you're talking about accuracy, if let's say the accuracy is 95%, but the sensitivity is only 80%, still affected because for medical purposes, if the sensitivity is 80 and above, it's still affected. So we can increase the sensitivity. Yeah? So I think in this case, we need to involve more pathology in validating the data, so that we will have a fair evaluation of the data itself. We can also involve data from internet, our self-collected data, and also the pathologists to validate our data. So that's in the process of validating our data is important. Thank you.
Prof. Looi, probably I can ask you one question. How do you foresee the training of our pathologists in future in order to meet the needs of digital pathology and AI in our country?
Thank you, Dr. Arnie, for that question. I know it's a question really from your heart. You're always thinking about how to produce enough pathologists for the country, and I suppose that's true for all of us. I would see that digital pathology and AI actually would enhance the training if we put our effort into developing good ground truths to develop really a robust AI system for our sort of our systems are basically. If we are able to adapt digital pathology into training, and I think we're just literally almost there, we can ensure, for example, that all trainees get to see through digital pathology the wide range of conditions that will help to train them. For example, at the moment, you can say that some posted to certain hospitals may see less of certain cases compared to others. But with digital pathology, you can actually enhance the training sets, the slide training sets, so that everybody can share and can see the type of cases. They see a larger range of breast cancers and so on, the rarer tumors, the variants and so on. So that's the digital pathology part of it. It is just seeing enough, seeing more, and we know the more we see, the more we learn. The AI part of it is not yet quite with us, but I think it is important, as have been mentioned earlier, that the input from various pathologists to develop robust ground truths is going to be important. The more input there is into the system, into the machine learning system, the better it is to be more accurate, to be more predictive, and also to adapt for changes in the future. Now, that may not impact so much on the training of our trainees, but they are the ones who are the future pathologists. So they will also be put into the system over time. And imagine if a machine is getting trained not by just 2 or 3 pathologists, but by 1,000 pathologists in Malaysia, how much more enriching it will be in terms of its ability to sort out variations and to be more accurate. And with that, it will finally input into the training system. So in the end, I think it will just, in a way, enhance itself. So I see that the future in adopting digital pathology and AI to be a very positive move for the education of our trainees, and also to reduce unnecessary workload for our pathologists, as I have mentioned in my lecture.
So,
I mean, in that sense, it may actually make it possible also for us to train more people and to train in a unified manner.
okay. Do you think artificial intelligence in digital pathology should be carried out as a national agenda? I'm posing this question to any one of you.
Well, should I try to answer that?
Sure.
I think as a national agenda and as a college agenda, as a agenda of pathologists as a whole, would be more effective than any individual agenda. You have to look at where it best benefits the country before we put our money into it. Right now, there are certain costs involved, and perhaps those who are involved in developing the hardware necessary and the software necessary would need to consider whether there can be ways whereby this cost can be reduced. And if it's a national agenda, I think the ability to negotiate for a reasonable cost becomes easier. Whereas individuals, I mean, what is the attraction to the market if you're just an individual, in the sense if you have a whole lot of a bigger market, many hospitals involved, many pathologists involved, I think it is more important. And that's addressing the cost issue. The other issue is addressing the interconnectivity issue so that you can have the correct platform. That all of us are going to group together and share how we learn and how we share the images or data or the whatever platforms. There have to be some commonality, the simple way I look at it. And if you make it into a national agenda, it becomes much more easier to address this. So just my simple way of looking at it. Good to know how the others think.
Okay, based on the Granada University Hospital, they mentioned that they need about 10 years to, 100% digital pathology to be implemented in the hospital. And they said that it's quite impossible if without involving government and the top person in the country. So it should be, the national agenda. It's quite impossible for us to implement it without their support.
Okay, yes, Dr. Eddie Huang, would you like to say something for the last 2 minutes?
Yeah, that's definitely, those are great presentation and great talk about the artificial intelligence for the digital pathology. My job is to support our AP region for the clinical hospital to get involved and to speeding up the AI development in clinical hospital. That's pretty clear that I see there are so many countries, they believe that AI could be the valuable toolkit. So that is the AI is a toolkit. Like, it's not like to replace some professional service job. Like, they definitely cannot help, doctors or the pathologists to make it even more double check, or they can reduce their professional time, or they can make more have some second opinion suggestions. In this perspective, I would say yes, and sure, why not? Let's go for the digital guys. Like you can see in another way. I was from the radiology. That's very clear. You save a lot of money to when the X-ray film going to the digital. So many stuff like you know, you don't have to do some time consuming redundant similar job. So for me, yeah, I would say definitely to go into the national agenda, especially I'm working in media though. Thank you.
Okay, thank you very much to the three of our distinguished speakers. As for me and Dr. Arnie, I'm sure will agree that we really enjoyed this session. There's a lot of things to think about, and you know, a future ahead waiting for us. So we would like again to thank you to all the speakers for your time for this symposium. And as a chair for this symposium, I would like to also thank the delegates for attending this symposium. And we hope that all of you enjoyed the rest of the virtual conference. Please try to spend time at the exhibition halls, the e-poster hall, and we have emailed the details to you to assist you in navigating around. I have many surprises for you, prizes to gain when you visit the exhibition hall. Okay, so be sure to visit them and make use of the information counter. This for you to gain the CPD points, for you to have live chats to assist with any of your queries, and e-certificates will be provided after feedback is received. Okay, so happy exploring. Enjoy the rest of the virtual conference, and thank you everyone. Have a nice evening. Bye-bye.
Thank you
Thank
to
you.
all the speakers.
Thank you.